Good morning. I'm Adrian. I'm the head of software of Planq. I'm one of the computer scientists here. And today I want to talk about taming atoms with code, software challenges in building a neutral atom quantum computer. Before I start, I want to briefly tell you a little bit about Planq. I'm not sure if everybody knows what Planq is. So it is a company, and we are a startup. We were founded in 2022, so it's quite young. We are we are the first startup that was founded out of the Munich Quantum Valley. We are already about 50 people, and our business models, I put it very simple here now, we build full stack quantum computers, and they are based on neutral atoms. So what does this mean? Mostly, we have like the upper stack. There we have already a lot of algorithm projects and software projects. Some of them, so not they were mentioned, but like in the same direction yesterday by BMW, like in the direction of battery material simulation, fluid dynamics. So there we have a lot of expertise in fluid dynamics on our algorithm team. It's also quite big. Climate models, material science, and also more on the software side, and a cloud platform for sure, and fault-tolerant quantum hardware is also important to really bring out the best of a quantum computer. But the bigger things we do are, for now, 2 quantum computers. They still have names. So one is called DNAC, which we built for the DLR. It will have 100 qubits. And the second one is called MAX. It's built for the LRZ. And it will have 1,000 qubits, so they are split up into multiple cores, so we will not be able to use 1,000 at one time. But that's basically very rough what we do. So let's have a look at our very simplified quantum software stack. In the end, what we have always, you have seen this a lot now, you have some quantum algorithms engineer, he or she wants to execute something on the hardware, and there are layers in between. Here we have like a cloud service, where we've heard in the previous talk already a lot, then a compiler, and then the quantum computer itself. And we will have a look today into these 3 things. One is controlling the hardware, which in itself is a very challenging software problem. Then sorting atoms, it's my favorite problem, so I've also brought it. Then the compiler itself. So here a lot of people interested in compiling, and compiling for neutral atoms is a little bit different. So there are multiple things you can also do there. But before we start, I want to give you a short introduction how a neutral atom quantum computer works. At least from my point of view, my computer scientist, people don't know how it works. You are probably far more knowledgeable, but I want to give everybody on the same page. Also, like the problems are very depending on neutral atoms. So let's look into the neutral atom quantum computer. Now we have a schematic. It's not so shiny anymore. And what you see here now, you have 3 boxes. They are connected. They are a big vacuum chamber. In the end, you have a glass cell. It's also part of the vacuum chamber. So you see these are connected. The left side there's an oven. You have vacuum pumps. And the goal here, basically, on this design is more or less, you want to have a very high vacuum. 10 to the minus 12 is a very high vacuum. It's similar-ish to the vacuum at CERN, and people told me that the vacuum at CERN is very good. I cannot tell you, it seems like very good. And in the end, what we do the calculation is here at the end, we'll see in a bit. And here we want to have the best vacuum, or like in this region, and this is how you can make this true. Let's have a look at the life cycle of one atom. So we see the whole life cycle of how things will work in a neutral atom quantum computer. So the atom is more or less born in the oven. So it's really an oven. It's some 100 degrees hot. You put in a block of, for example, strontium or ytterbium, like the material you want to use. And then there are a cloud of these vaporized material exits the oven. What you can do now is you enable multiple lasers, so there will be a lot of lasers, to capture atoms. Like the first stage is called 2D MOT, two-dimensional magneto-optical trap. So there are also magnets around, and with this you can trap atoms. So they are already quite cold in the millikelvin regime, not cold enough, but you can trap them. So you really have like this small called cigarette, like it's 1 centimeter wide and 3 centimeter thick. And because we only trap in 2 dimensions, so like it's 4 lasers, laser beams, and we can only see 2 because it's like in the plane. It's not trapped in these regions, so it's basically has this shape like this. What we can do now is we can enable the push beam, which does exactly this. So it pushes the atoms into the glass cell. Here we have another cooling stage, or it's actually multiples, and it's like the 3D mod. And here we cool it even further. So it's now in the micro-Kelvin regime. And what we can do next, maybe this is how it really looks like. It's a picture from the Max Planck Institute. You see here the glass cell around, and this very bright spot is the cloud of atoms. So it's 1 millimeter sphere, and if you shine the cooling lights on it, you can really see it by eye. It's really impressive. Like it's a very blue, like it's pure blue, at least in the case of strontium. What you need to do next, because like it's just atoms floating around, here you see like a magnification of this. You add more laser beams, and there are multiple ways to trap single atoms. Like this is now just to explain a very simple one. You have like multiple laser beams, and they are focused in this focus plane. So they basically here they go to a minimum. If we zoom in to exactly this this part, a laser beam looks like this. It does not go into infinity small. It has this waist, and exactly at this waist you have the maximum intensity. In this intensity you can trap single atoms, and this is basically how to trap an atom. So now what you want to do, you want to take a picture from the camera. So now we have a plane of trapped atoms, but it looks like this, so you cannot, or it's very difficult to do computation on this, so you sort them. And then, for example, you can get a grid. It does not need to be a grid, you can do whatever you want, but like a grid is the most easy one for the beginning, with a 3 micrometer distance. Just for comparison, like a hair has about 70 micrometer thickness. So everything is on a very short, so small scale. Now what we actually want to do is the calculation. So how can we do this? We can address these atoms individually. So basically we can shine a laser from the direction out of the plane here now on one of these atoms, and with this we can do a rotation like single qubit gates basically. If you want to do multi-qubit gates, there's the so-called Rydberg blockade, or Rydberg, because it's a Rydberg atom. So basically what you can do is you shine another laser on it, and you go into a very high energetic state, and with this you can do interactions with near atoms. So in this case you can do an entanglement between these if you want, and if you use this, but if it's too far away it will not work anymore. So in the end we want to have a measurement. This also works by just taking a picture again. Now you see some spots are dark. The dark ones are not in the state you are measuring in. So basically these are all ones and the rest are zeros, or we lost the atom. This can also happen. So then the qubit is not there anymore. There are measures to also see if you've lost it. But yeah, that's basically how a neutral atom quantum computer works in very short. And now let's have a look into controlling the hardware. Because for computer science point, this is very interesting. So what we have, so you've seen how this works. Basically, from this point of view, a quantum computer looks again a little bit different. So what we have is a control computer, like this is the entry point for quantum engineers to the cloud platform. And this classical computer basically coordinates all these devices. So there's a camera we've seen before, there's a timing device, which is just a device which has very good timing, and multiple other devices. Like there can be tens, so multiple ones, and you need to coordinate them very well. And this looks more like this. I'm not sure who has played Guitar Hero before, but it's basically the same. You have a timeline, you have some channels or some knobs to press, and you need to do this very precisely. And this is now, I think a very simple way. It's quite long, 5 seconds. And in the end, what you have, like each line is a device or a property of a device, and you need to change it multiple times, sometimes multiple 1,000 times in a very short amount of time to make exactly what we've seen before. So what are the challenges in building this? So there's many different devices. They also work sometimes on Windows only, sometimes only on Linux. So that's a little bit annoying. Then you need to control them really in parallel, like we are talking about nanosecond precision. This is not easy. You want to have, for sure, high repetition rate. The faster you are, the better is the utilization of your machine. And in the end, it's a lot of data, like you take a lot of images. They on its own are not very big, but with the high repetition rate, it gets a lot of data. And what you really don't want to do, don't want to do have an error during your sequence, because then things can break. So this is everything you want to build into the software, so it's very challenging, but also very fun. And how you could tackle this, or you can tackle this, or it's not the only solution for sure. For the hardware devices, you basically build a modular system where for each device you just have an API, or a global API, and with this you can plug and play new devices into your system. For parallelization, multiprocessing is great until like microsecond precision, but then this is not good enough. Then you need an external timing device. High repetition rate, so you need to parallelize a lot of it. And basically you try, while something is running, you prepare already the next step and you pre-process the previous one. So you try to make this really in parallel. And data acquisition can be done decentral, also like the processing can be done decentral. And in the end, the verification of your sequence can be done by simulating it. That's also quite challenging. But with this, you can make more sure that it will not break your machine. So this is basically the challenges in controlling the hardware. So we are working on this now for a bit. We don't use any other software from outside, so we build this on our own so that it fetches our needs. When the hardware can be controlled, we can also start sorting atoms. So what does this mean in the end? We have seen this before, like we have this unsorted atoms, and we want to have this sorted atom array. And in real life, this looks more like this. So on the left side, it's unsorted, here it's more like sorted. And this is for sure more challenging. So there are basically 5 steps how to do this. First step, taking a picture. That's already wonderful. Then we extract the occupation matrix, which means just for each possible point in our quantum computer where an atom could be, we put a 0 if there's no atom and a 1 if there's an atom. So then you get something that the computer can understand better, like it has so less data. Like this translation is already a complex problem because you need to make it very fast and very accurate. This also looks more like this. If you have like a very high loading rate, so this is from the Max Planck Institute, from Strontium Rydberg lab. They are super advanced already. What you can see here in the red square is basically this. And you see here already 1.2 thousand possible spots one atom could be. And in total here, it's more like 10,000s. And basically also you can see here like scaling for neutral atoms works quite well. Like these are not qubits, these are all atoms for now. To convert them to qubits, you need single addressing. So, but yeah, there is potential to scale to a lot of qubits. Now after the occupation matrix you have extracted, basically you have a need to do a sorting strategy. Basically what this means, I guess now very simplified. You have like this grid of 9 by 9 possible sites where an atom could be. It's blue when there is an atom, it's red when you want to have an atom there, and if it's green if you want to have an atom there and it's already there. So what you need to do is to assign to each of these spots an atom. And best way, the closest, not always the closest, but depending on your cost function, the one that will probably not get lost, because if you move an atom, it can be lost. If you do turns, it can be lost. If you move too close to another atom, it can be lost. So going directly straight here is not a good option. So if you look into this into more detail, it's basically the same grid. You can go in between sites with an atom, go around and then go back. And with this small, it looks like a toy example, which you have in computer science class that you need to solve to get some points. But really, this is super important for us. And this needs to be done very fast. Because in the end, you have 1,000 atoms you want to sort, or like 1,000 spots, and around also at least 1,000 or much more possible spots. So if you combine these numbers, it's a big space where you want to search the optimal path. And also here, like with the loss function here, you see it does not always get the nearest one, because like making turns is expensive, or then you can lose atoms. So here like you have like these long stretches, an atom can go directly to another site. But this is not an optimized version. So in the end, if you have this, also then you need to calculate instructions. Basically, you have a multitone that you can then execute on an arbitrary waveform generator. And then, if everything worked well, you can go directly to circuit execution. But probably, at least at the beginning, you need some rounds until everything works perfect. Because the more atoms you move, the more you will lose. Also, taking picture, you will already lose atoms, and you need really a really good grid that you can do good calculation. So here's like a short video of how this could look like. It's also from the Max Planck Institute. You can see here basically just images and rounds of sorting, and you see at the beginning it's chaos, and then it emerges like a kind of rectangular grid, which is also not yet perfectly filled, as you can see. So now the last point is compiling for neutral atoms. What you want to have in the end, again, someone has, for example, base state circuit in Qiskit, and they want to execute it on atoms. And you can divide this in 3 steps. Platform-independent compilation, which is basically what most of you already know. If you have 2 X gates, you can cancel them out, or things like this. You don't care whatever is below. Platform-dependent, then it's neutral atom-based. This is what we have a look into it now. And then hardware-dependent is really based on the hardware. So for example, translating whatever comes out here into the sequence we've seen before, like this beta hero sequence, which then can really be run and executed on the array. Everything now is highly inspired by this paper, Computational Capabilities in Compiler Development for Neutral Atom Quantum Processors, Connecting Tool Developers and Hardware Experts. So if you are a computer scientist and you want to look into compilation for neutral atoms, I really recommend this read. It's really good and gives a very good insight into this. And I think there's a lot to explore out there. There's not a lot of neutral atom compilers out there. And let's have a look into it. Also, this picture is basically stolen from this paper. It's literally a screenshot of it. So how does it work? At the beginning, we have unitaries, like circuit with big unitaries. And what we want to do is to compile it into a native gate set. So basically, a universal quantum computer can have a native gate set, and with this you can translate every unitary in this native gate set. And this is the first step, it's called synthesis. And there's also some challenges. Each quantum computer could have different native gate sets. For example, some neutral atom quantum computers have in their native gate set global gates, and this makes it very interesting to process here. Next part is the mapping, also known from other platforms. What you want to do, like here in green, you have neutral atoms sitting around in space, and you want to map the circuit qubits, which are denoted in a small q, to the physical qubits. Physical qubit 7 is this one, 2 is here. And this is challenging for sure, because not always does it work. But let's have a look. Here it kind of works very good, like the gate 0. You want to apply to gate 7 and 5, they're next neighbors, so you can do, if the Rydberg blockade, you can create like, you can execute this gate. Like single qubit gates always work, so on qubit 6, that's fine. Here's a 3 qubit gate also in it. Although this works, like they're also very close to each other. But if you now look into this one, and this gate, you can see they are too far apart, so this will not work. And what you can do, you can just exchange these atoms. So you add a move operation here, so you can move atoms around during execution, and this gives you a lot of freedom. Basically, with this, you can get more or less an all-to-all connection, but you need to move atoms physically around. This costs time and can cost you fidelity. So you always have to make a trade-off between, do you want to have a move or a swap operation, and also a compiler can basically then figure this out. And the last part is scheduling. So this is really timing based. So on the x-axis now you have timing. So you see move operation takes quite long. And this is also critical because you want to have like a short circuit. Like again, you have a cost function with multiple objectives. You want to have a short, not so many gates, depending what gate you want on your architecture. If you have a global gate, you can parallelize. So if you have a global gate in your native gate set, then you can parallelize here multiple things, and things get very complicated. So also what I brought, which is also not from us, it's also from the TUM chair of design automation, from Yannick and Lucas, is basically they already have a compiler for neutral atoms. It's quite interesting. And they have also a tool to animate it. So what you can see here at the top, there's like an entangling zone. So there's also something you've seen probably from Qera before. You can have zones, also a readout zone would be possible, it's not here, to have a partial readout in between. And here down you have the storage zone. What you see soon are blobs in this color, and this is where then atoms are. And if you see then these colors, you see that it's a single qubit gate, and the entanglement with this orange color will be done here. So let's get started. See now very many single qubit gates are executed. Then you can move around atoms to do a 2 qubit gate, and now 1 qubit gates again. And this is a QAOA algorithm that they mapped basically in this compiler to this version. And this now could be executed. It also looks like in simulation how it would work on a neutral atom quantum computer in real. So that's all the 3 topics we wanted to cover today. Thanks a lot for your for your attendance. And if you're interested in one of these topics, it's very interesting. There's a lot of research going on, also here in Munich at Robert Wilder's group. And also, if you're interested, feel free to approach me. And yeah, thanks a lot.
Thank you.